So let us begin. This is lecture 7, I think. And we're finally getting into some fun stuff. At least I think it's fun. And we're actually learning about supervised learning now. And so how today's lecture is going to go is I'm going to kind of review a little bit about what we did last time because it was quite important. And then after that, we're going to jump into a particular detail, like high level, there's this ERM algorithm. There's estimation in it and optimization. We're going to really focus on this like estimation part today. We're going to kind of jump into the details of how that's going to work. And in the following class, we're going to talk about optimization. And at the end of next class, we'll finally have our first actual algorithm that you can run on a computer. And it won't be that exciting, but it'll be something. And that's what things are going to look like today. Okay, so let's remind ourselves what was going on. So the story was something like, we had this data set, and from the data set, we somehow wanted to produce a good predictor, which means like if I'm given a new feature, I want to predict the label correctly, roughly speaking. And we had this like ERM thing, near free lunch. I'll go over it in a second, but I thought, why don't we just like draw like a plot of some things, you know, to maybe have another view of how this is all related. And then we'll jump back to the ERM thing and see how it's kind of the same story. Okay, so let's do house price prediction stuff again. But this time let's make it like the x-axis, you have one feature. I guess there's a question, yeah. Oh yeah, I wanted to mention this. So as you might have noticed, there's no notes for today, and that's because honestly, I'm just going to write like 4 or 5 pages live, so there was nothing there. And then I'll share it after class. Yeah, that's that. Oh, another thing I wanted to point out is if you, I don't know, if you were paying attention last lecture, you might have noticed that the explanation I kind of gave or the story is a bit different from the actual like course notes PDF. And yeah, that was just me. I decided to try to do it a slightly different way, which I think was kind of hopefully better last time than the previous years. So you'll have like 2 views. If you read the course notes, it's slightly explained in a different, like you get to the same algorithm, but like the story was kind of differently explained. Okay, so that's just so you know. Okay, so here we go. We have our example of predicting houses again, but this time we'll pick the feature to be like the size of the house. And you know, like the size can be like, let's say any amount of square feet. So it's like this continuous value from 0 to possibly infinity. And then imagine you had your data points. So these are like, I don't know, you gather a bunch of houses. This is all these points. These black guys represent your data set. And I guess this is like a particular instance of your data set. So I usually use this like calligraphic D thing for that. And okay, so you see this data set and you're like, if I get some new point, and let's label the new point like, I don't know, this guy here. Then I want to predict that well. And that could be like anywhere in here, you know, the new point could have been here or something like that. The question is like, how do you do this? And what I want to like point out here is that that this ERM algorithm is doing kind of the obvious thing, right? Which is like, okay, you need to pick some function, right? And like to predict things in the future. That means like I'm going to need to assign a value for literally every single point on the x-axis for what I'm going to predict. So like there's all sorts of functions, you know, I can pick this or that. And so let's just constrain ourselves to like picking a line. Like, but we need to pick, there's lots of lines, so we need to pick a particular line. And so you can imagine that like what you will do is you will search over all lines. And like, I don't know, let's draw some lines. So maybe this is like a line. And like this is, I don't know, another line. All sorts of lines. And then, okay, I'll draw the obvious. Maybe I'll draw this one in green because it's kind of like the one that you probably want to pick is this. And then the question was just like, okay, why is this the one we probably want to pick? And it's like, okay, let's somehow measure the quality of this line. And the idea was to like measure how well does it do at predicting points in our data set. And then I was like, okay, let's take this line and look at its prediction for every single point in the data set. And let's have some measurement for how far it is away. So that'll be kind of like this red line. And we take like a distance of this red line and this one and this one. And okay, you understand the story. You do the same for all the black points. Maybe I'll draw a few more. And this measurement here of how far your prediction, right? Your green line is what you would predict, and this is the actual value you saw in your data set. This kind of measurement is exactly like the loss of what your function would predict at, say, maybe this is like a point x prime at x prime relative to the true value, which I'll label as y here, so compared to y. And so this loss function is just like the way we measure this distance, and the way I kind of drew it here, you might think this is kind of like the absolute value loss maybe, because it's just like the measure of distance. And so that would just be like f of x prime minus y, take the absolute value. So if you have points underneath, you still suffer error. If you have points above, you still suffer a positive error. Okay, so this is the story. And then what you do, right, is like if you're searching over all lines and you want to minimize this guy, well, you're going to want to minimize it over like all of the data points. And that's exactly like your estimated loss over all the data. We have this estimated loss or empirical risk, and you want to make that as small as possible. And so what you're going to do is like intuitively is you would look at this line and be like, well, what's the error of this line of predicting points? And you'd be like, oh my God, it's ginormous. Like there's all these, it's terrible, right? And then anyways, so the story is you go through all these lines, and maybe one way to think about it is like if I drew it like this, you could have this lot, you could like search over all lines. So you're like sweeping, you're calculating the errors of them. And then you get to this guy and you're like, oh, that has so far the smallest value. And then you pass this point and it gets larger and larger. And you're like, okay, that is the line I should pick. And so how this maps to kind of this whole UofA thing is that, you know, your function class, so we have this thing called a function class. That was like this calligraphic F. Well, in this case, it's just going to be, and I'm just going to put in words, which is like all lines. Well, we know how to write this. And that's what we would have done. So then UofA would have just searched over all these lines and tried to minimize the corresponding loss over all of our data points. Okay, so that's the idea. And now let's kind of like formalize this a little bit more, remind you of the formal story. Yeah, so this little function was like a measurement between any data point. But the problem is that, once again, these orange new data points could be coming anywhere. And somehow we want to like talk about how well we're going to do on this like random data point. And so we take like the expected loss, right? And so that's what this L of F guy was. This was literally, if we just scroll up again, we can have a look. Yeah, so this L guy right here was just the expected value of the loss, and this is the expectation over like new feature label pairs that you would see. Okay. And so then UofA is like, okay, I kind of like want to minimize this. And so how am I going to do that? Well, you're going to use data to estimate this quantity. So that's why we had this like data set. It's a rough estimate of what you would expect new data points to be. You know, like your new data points, orange points, should be like roughly what you saw as your black points. If you have enough black points, then, you know, it probably covers it pretty well. And so we're going to talk about how to estimate this. It's going to be kind of obvious, but there's going to be some details to build our intuition mathematically. And when we do this whole estimation, we need to estimate it for every single kind of like predictor we want to consider. And all the predictors we want to consider, all the functions, all the predictors in our function class F. So those are lines. And then once you have this estimate of what you're going to do on like future data, well, the obvious thing to do is then just pick the line, pick the predictor in your function class that will minimize your estimated loss. Okay. Hopefully that makes the story obvious. And then really the crux is how you implement things. And really a lot of it is in this optimization step, which we'll talk a lot about. Some other high level points, just so like you guys, you know, you might go out into the real world, or you might run into someone on the street and they might be like, what are you using for your machine learning algorithm? And you're like, UofA. And they're like, what? And most people in empirical world might not have heard of this UofA thing. And yeah, people will just call this whole process kind of like, I don't know, I'm like doing supervised learning with gradient descent or something like this. This is like a common terminology. And really that just means you're doing gradient descent for optimization here, and then you just kind of don't even discuss the estimation thing because it's always going to be the same thing. What you'll see is just taking the sample mean. And so people will be like, yeah, I'm running like gradient descent, or like I'm using gradient descent with my function class that's like neural networks, for instance. Or like I have convolutional neural networks or transformers. And these are all things you hear in machine learning world, and all that they are is like different function classes. So we're going to talk about picking your function classes and so on in this course. Okay. Another thing to maybe mention is I just wanted to kind of like dig into a little bit of notation about things, so maybe unravel some things. So we talked about, okay, at the end of the day, we don't really know like what data set we're going to get. It's random. It can change. And if that changes, then the predictor we're probably going to output will change. And so we're going to want to care about like the expected value of our risk. Right, and then we had this like equation like this. And let's just unravel this equation by just literally writing the definition of what this object is, and just see a couple things and how we like slightly may have abused notation earlier, which may have confused some people. Okay, so what's going on here? So first of all, we clearly have the outside expectation. And now I'm going to write the inner term, right? Well, the inner term is the expected loss. Okay, so that's the expected value of your little, like your loss function that compares your prediction to like the true label. So that was over the random x vector. Oh, that's not how that works. You take your predictor, and we wrote something like f hat here, okay? And then we said takes in your random loss or your random feature vector, and it compares it to your label y. And we had this guy in here like this. Okay, how does this work? What is going on? So there were some things that you had to map in your mind or understand to make this notation kind of work. But remember one thing, which is that we said, first of all, that our learner, when it takes in a data set, it outputs f hat. And implicitly we were like, oh, f hat is, you know, the thing your thing outputs. And we just kind of forgot about this and just talked about f hat above until we got to this point. Okay, and so you have this. Maybe to make it slightly more clear, the way you could write this is, and this is like, I guess, makes kind of like shows you some extra details about things, which is really what's happening here is you have your learner, which takes in a random data set. This guy here produces a function f hat, and that itself will take as input new features, and then you compare it to new things. Okay, and then people will often to like decode this expectation stuff. People will clarify what the expectations are over, right? So like this guy out here was over like the data set, and then this inner one was over these features and labels. And so people like to write the fact that the inner one is like conditioned on your data set. And so this is how you would write it. And the way to read it is like, this expectation is like your weighted sum over data sets. And then for each data set, which is what conditioning means here, you fix like each data set, and then you take the corresponding expected loss of your predictor that you output for that fixed data set. Okay, so hopefully that kind of unravels a little bit of the notation stuff. Okay, that's all I want to say about that. And that kind of wraps up this. I'll upload this updated, slightly updated version of the notes. And then what we're going to want to get into now is this estimation stuff. But before we actually get there, I thought, why don't we go back to the probability section? You might have remembered I missed an example, or I skipped an example that I said I'll come back to. And it's like deeply related to what we just did here. It's really going to work out a calculation. And that might be helpful to see how that works. So I'm just going to jump back to the probability section. And what we're going to do is we're going to work out an example of calculating this expected loss, this actual risk function. So we're going to calculate this guy here. Okay, well, what that means is I'm going to tell you, like we're going to pick a distribution over x and y, and then we're going to do this calculation and see just what it looks like. Okay, so that was like these probability here. And this was the example. And let's jump into it. Okay, so here's our problem. So you have features that are one-dimensional, numbers from 0 to 900, and you should think of them as the amount of chemical, some chemical in your wine. And Y is your label, and it tells you whether your wine is this Barolo or not Barolo wine. Okay, and now this is just given to you, okay, in real machine learning, you're not told what this distribution is, but we're going to do the example where someone actually tells you what the true feature label distribution is, and then we're going to just calculate this expected loss, the risk, of a particular predictor and just kind of see how the calculation looks like. At the end of the day, we couldn't do that. If we could, we would have just done that for every predictor and picked the best one. We're going to need to estimate it, but here's just an exercise to see how the calculation would look. Okay, so I want to define P of XY. Maybe this is some PMF, maybe it's a PDF, maybe it's a mixture. In this case, it's going to be this mixed thing because you have a continuous random variable and a discrete one. And it will be sufficient to tell you the corresponding conditional of y given x and the marginal, because these are equal. And that's what I'm going to do. And this also gives you some more intuition of how the labels are related to the features. So first of all, suppose the features, that kind of PMF, follows a uniform distribution. Okay, so that means something like this. So, okay, this is a PDF, sorry. And it has a uniform density. So this is the density here, and it's just splitting. So what that means is that the amount of chemical you can expect to get is just any number between 0 to 900, you can expect to get each one equally often. Okay, now how does our label relate to our feature? Well, the statement here is that, and I suppose this should have been the actual distribution, right? Because this is the distribution. Little p is used for the PDF. Okay. And so the way the labels are related to the features is that they follow, okay, a Bernoulli distribution with parameter x over 900, where x is your feature. So what does that look like? That, remember, a Bernoulli distribution, this parameter tells you the probability of getting 1. And so explicitly, this means that the probability of you getting a label of 1, so meaning a Borello line, that probability is x over 900. And that's to be interpreted as x increases, as the amount of chemical increases, the probability of getting Borello line also increases. So that's kind of the relationship you have with the labels and targets. Okay, and now here is because we didn't learn about losses and stuff, I just wrote this as a general function. Let's rewrite this to decode it in our new notation now. So here's the story. So we're going to have a predictor, f, okay? It's going to take in x, a feature. And here's I'm just giving you just some predictor. And maybe it has some intuition behind it too. What's a reasonable predictor? Well, maybe I should just, given some feature, maybe I should just predict Borello with the corresponding probability of it actually being Borello. So here's my predictor. It's going to predict x over 900 as the corresponding label. Okay. Okay, and so now this guy here, this should be the loss actually. And the loss, if you remember, takes in a corresponding predictor and a label, and it compares the two. And so this guy in here, this x over 900, I guess I can just move it. Yeah, okay. So all we've done is plugged in this value in here, and we chose to use the squared loss. And the thing that I have realized as I was writing this is a little bit odd. We'll actually see that we do this in the future for various reasons. But notice how we have a classification problem, which has labels of 0 and 1. And I told you that we should use the 0-1 loss, which is you either get 1 if you're right or 0 if you're wrong. And then now, and your predictor here is kind of weird too. It's predicting some probability instead of the actual thing. We'll see that at the end of the, we'll see this is a little bit of abusing things. I'm not going to change it now, but later on when we do classification, we'll see this is actually how we're going to do classification. We're going to actually just solve the corresponding regression problem and use a squared loss. And then after that, based on what our predictor outputs, if this is greater than 50%, we output 1, and otherwise we output 0. So just, this should be confusing. If it's not, you probably didn't see what happens. But anyway, so let's just imagine we have this regression thing. We're using the squared loss. Let's just do the calculation. And in like 5 weeks' time, we'll understand why we're doing this for classification. Okay. So yeah, now I just want to replace some of this calculations. So this F guy is now the loss of the predictor compared to the label Y. And what is this object, right? This was like our capital L, the expected loss of our predictor F that we saw earlier. And to do this calculation, you would have to like explicitly write out the expected value, and then you would go to your probability review notes, which are going to be on your formula sheet, and you would notice, okay, like, you know, P of Y given X is discrete, or it's a, like, this is the PMF, right? Because it's a discrete random variable, Y given X, and this P of X distribution is continuous, and so I have to use this like formula, which is basically I break up the corresponding mixed PMF PDF thing into these two terms. And you would see this on your formula sheet, which is you integrate over the features and then you sum up over the labels. Over your function, which is now going to be this L guy, your loss, of your predictor evaluated at X. So this is to be read as you like fix a particular feature and then you calculate the loss you would expect over all the labels of your predictor, and then you take the corresponding weighted sum of the corresponding features you would see. Okay, anyway, so this is useful to know because you're going to need to be able to calculate these things. And then afterwards, you really just plug in the corresponding definitions that you've been given, which is like P of Y given X was given some definition. This is a certain definition. The integrals are over the entire like X and Y sets. And so after plugging all that in, you can do the calculation. You'll do it in your assignments and probably on the midterm. You do some calculations, you get a number, it's 1/6. And this tells you the expected loss of this predictor, which predicts like X over 900. Okay. And then you could do this calculation for all sorts of other predictors. Like you could have chose a different predictor, like, I don't know, maybe you chose X over 500 for some reason. I don't know. Or maybe you chose like a constant number. Maybe you chose like 0.5 or something. And then you could do this calculation and you can then see, oh, okay, this has some error, this other predictor has some other error. And like if you really knew this function, you would then just pick the predictor that minimizes. And it turns out for this example, actually, this is the smallest loss you can achieve, and this is really the best predictor. And it sure makes sense because it just predicts exactly the probability of getting. Okay, so that's all I want to highlight. So let's jump into the whole estimation business. And just to remind you one more time, what we're doing now is in supervised learning, we had this ERM algorithm learner, and we're going to focus on how are we going to estimate this expected loss, which in the previous example we calculated. We can't just do that explicitly because we're not given these distributions. We're going to try to estimate it. Okay. That took a little bit of time, but hopefully that was useful. So we're getting into, okay, how is this going to work? The way this is going to work is I'm going to give you a nice simple example of how estimation would work with coin flips, like n coin flips, and then we're going to just kind of map this notation and intuition to the loss functions, taking in random features, random labels, and you'll see that hopefully that mapping makes everything a lot easier than just jumping to it immediately. Okay, so this is a whole topic in I guess statistics, and there's a lot of ways to estimate things. We're going to do things very simply, but we'll learn some things. And so roughly speaking, you could think of estimation as this process of using some data, in our case, our data set, to, approximate a fixed number, usually, or some fixed quantity. But in our case, it's going to be a fixed number. And most of the time, it's going to be you want to approximate some parameter or something like this, or maybe, yeah. Okay, so let's have a look how this is going to work. And just in words, an example might be that you want to estimate the expected value, sometimes called the mean, right? Of, say, an unfair coin. So you have this unfair coin. You have no idea what's the probability of it becoming heads or tails. Sometimes people call it a bent coin. So you can think a coin has been bent and it's maybe more likely to fall on one side than the other. And how are you going to learn what's the probability of this? Well, we're going to use some data, which is a bunch of coin flips, to learn this. And let's formulate this with our new, well, not our new, but our language of random variables and probabilities, and try to write this out more formally. Okay, so we have this uniform coin, or sorry, unfair coin, not uniform coin. And we're going to use a random variable to describe it, like x. And the values it's going to take, right, are 0 or 1. And so this is going to be, as we have seen before, tails. And this is going to be heads. And the reason we use numbers here is so that we can actually, compute things like expected values and so on. Because if we just use the words, you wouldn't be able to multiply things. Okay, so what is our coin? Well, our coin, like this random variable, has some distribution. So we would write that this random variable is sampled from or follows distribution P subscript x. And since it's a coin and only has two outcomes, there's really, the name of this distribution is called Bernoulli. And it has a parameter called alpha, which is the probability of getting heads that we've seen hopefully enough times now. And just to drive that point home, the corresponding, we'll keep it. The corresponding PMF, which takes in a particular outcome, such as the outcome of being 1, it's going to have probability alpha. And then P of 0 is the other case. Okay. So now we care about the expected value. So let's just, assuming we knew this alpha, let's just do the calculation so we know what it is. We've done this before, which is the expected value of a random variable, the coin flip, is equal to, right, the sum of each outcome times its probability. So that would be 1 times the probability, which is alpha, plus 0 times the probability, which is 1 minus alpha. And so this gives you alpha. So unsurprisingly, the expected value, which you should think of as kind of like the average over infinitely many flips, is alpha. If this was 1/2, then you take the average of like 1 and 0, it's 1/2. Okay. And so this is going to be the quantity, which is just a number, right? Notice this is the expected value, just gives you a number. We're going to try to estimate this. And so we're going to try to basically solve the question, which is like, what if we didn't know the expected value? How are we going to calculate this guy? Okay. And the story is kind of obvious, which is you're going to flip the coin a lot of times, right? Notice how this is already sort of mapping to our supervised learning setting. Like, if I knew this distribution, I could just calculate the expected value, and then I can do things with it, but I don't know it. But I have the coin, and really what that tells me is I can flip it a bunch of times. I can gather data, which is like, I have the Edmonton house prices. I can go gather, I have Edmonton. I can go gather house prices. And now I'm going to use that data to somehow estimate this thing. Okay, and now we need to it's almost obvious what you're going to do, right? You're going to flip it n times, and then you're going to take the average. But let's formulate it in mathematical notation, because you'll see that maybe it's not as obvious as you think, some of the claims. Okay, so here's going to be what we're going to do. We're going to flip the coin n times and take the average. And once again, we're going to try to formulate this more precisely. And so this is going to look like this. So now we're going to have a random variable x1 to describe the first flip of the coin, another random variable x2 to describe the second flip of the coin, and so on until we have n flips. This is a multivariate random variable that is an element of, 0, 1, this set. It takes either 0 or 1. And you should take Cartesian product it n times. And you can see that when you do this thing, you get a set of tuples of length n, and this is one particular instance. Okay. Maybe we'll use this notation. We'll see in a second. I can, as people like to do, give this multivariate random variable another name like z. Okay, what other assumptions do we have here? And this is us trying to formulate the intuition of flipping a coin. Well, when you flip the first coin, let's imagine you flip the coin again, but you don't look at the outcome of the other one. So you just keep flipping the coin basically. And the intuition of this is that the flips are independent of each other. Okay. And so the story is going to be that each one of these xi's, first of all, comes from a Bernoulli distribution. Which Bernoulli? Well, it's the exact same Bernoulli as we saw above with the same alpha. It's the same coin, right? So notice it's coming from that same Bernoulli. Great. And they're independent. And that's for all I. Okay. So far, should be kind of obvious. Okay. So we've got these n independent coin flips. Now let's take the average and make that our estimate of the corresponding expected value. Okay, so this is the function we're going to want to do. We're going to want to take the first coin flip, x1, and we're going to want it added to x2, and so on until xn, and divide by the number of coin flips n. Okay. Using some note, like let's practice all sorts of notation we've seen. You can rewrite this as the sum from I equal to 1 to n of xi. This is a lot more compact, divided by n. You'll see this often. Also notice that this itself, it's a sum of random variables divided by n. That's a random variable. And that's actually it's a function of n random variables. So we can write that this is a function, let's call it g, of x1 up to xn. All right, so now we've got this kind of complicated looking function of n random variables. But that's, if we're comfortable with our probability, this should be no problem for us. And sometimes people will like to, not explicitly write this as a function. They say, oh, this is another random variable x bar to signify that it's the sample mean. And another notation which people use, and we will actually use more often, is that you will write that this new random variable is the parameter you care about, or the value, the number you care about, with a little hat on top to basically signify that this is an estimate of that true thing. So since we care about alpha, you'd write a little hat up here to point out that this alpha hat is itself a random variable, and it is an estimate of actual alpha. And also at this point, you'll see why instead of writing L of f, the estimate was L hat of f. And we'll see that mapping in momentarily. Okay, great. So far it seems like we haven't gotten too far. But now let's look at something which is interesting, right? Which is every time you flip this coin n times, you could get a totally different outcome. And some n flips are more probable than others. And you might ask, okay, this value, this is going to give me a number, right? This sample, this average over my n coin flips. What is the expected value of this quantity, which itself is random, right? So that would mean something like, what is the expected value of alpha hat? And notice we can take the expected value of this thing. It's a random variable. It's the sum of n coin flips divided by n. Okay. And the calculation will require some of the properties from expectations that we've seen before. And so this is perhaps the point where I've noticed that things maybe start to get a little funkier and some confusion happens. Okay. So once again, just remember the fact that if you flip a coin n times, those outcomes can change, and we just want to calculate what is this expected sum we're going to get. So let's write it out explicitly, right? What is this thing? Let's take this quantity, plug it in. So this is the expected value of literally this. And now, you might recall that there's some properties of expectations that are going to make this a lot easier to calculate instead of writing out this whole thing explicitly, which we also could do. One of the properties is that a constant, which here you should think of, okay, let's write this maybe slightly differently to make it even more obvious, which this looks like this sum multiplied by 1 over n. This is a constant, and if you have the expected value of a constant times some random variable, it's equal to the constant taken outside of the expectation multiplied by the expected value of the random variable. And this thing's a random variable, the sum of n random variables. Okay. And now you might have also remembered a property, which is something called the linearity of expectation, which is if you have the expected value of a sum, then it's equal to the sum of the expected value of each term inside. And now I'll use some of the summation notation again to make this easier to write. This is going to be the sum from I equal 1 to n of the expected value of each one of these individual xi's. Right. So far we just used properties of expectations. Now we're going to use a property of the assumptions, or like we're going to use some of the assumptions we made for this problem, which is each one of these xi's follows a Bernoulli distribution, the same Bernoulli. So what that means is all of them have the same probability distribution, which means that all their expected values are the same, right? If you just write it out explicitly, you see that the only thing that changes is the p, and the p's are the same for all of them. So you can actually write that this is equal to 1 over n sum I equal 1, and you can pick any x, any I here you want. It's all the same. So I'm just going to pick the first one, which is commonly done. And then you notice that this sum is not summing over anything anymore. It's just summing over a constant. And if you take a number, a constant, you sum it up n times, you get n times the constant. And so we get this wonderful result, which is that n over n, the expected value of x1, which is just the expected value of x1. And notice I could have chose for I anything. I could have just chose anything. So I could have, this is also equal obviously to the expected value of x2 dot 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 the expected value of xn. Okay, what does this tell us? It told us kind of something sort of obvious, which is that on average, or like the expected value we would expect of this calculation that we had is actually the true expected value of every one of these coins. And maybe the important note is that this is actually equal to alpha. So this is wonderful. So the sample mean estimate has this property that, you know, on average, when you do the calculation from n coin flips, you will actually get the true expected value. Okay. Now here's a second quantity of interest, which is like, okay, great, you can get the expected value, but like, you know, how likely is it you're going to get the expected value? Or like, you know, you flip this, maybe like, okay, here's an example of when you might get the same expected value, but it's like very odd, and I'll kind of erase this, I guess, afterwards. Maybe like you always get, so you either get like maybe your calculations for alpha hat, you only get the numbers 0 or 1 with probability 1 over 2, which is not the case here, but you get this. And maybe alpha is exactly 1/2 here. Well, this is kind of unfortunate. It's like you calculated alpha, and like you're going to estimate 0 50% of the time and 1 50% of the time. And like, yeah, if you take its average, it is going to be indeed in the middle, which is this. But that's like quite undesirable. It would be nice if like, you know, maybe something like this, you know, like if you plotted like the points or the corresponding like PDF of the value of alpha hat, which is just a number, it would look something like, you know, like very, very rarely you get something here. You very often get a value around here and like this. And intuitively, what's going to happen, right, is that if you have only a few coin flips, then this thing is going to be kind of like spread out. And if you have a lot of coin flips, it's going to be very tight. And we're going to try to like formalize this a lot better with some math and another, I guess, example of just flipping a coin 5 times. And I just want to point out this variability and what I mean by it. Okay, so that was if you didn't understand that perfectly, don't worry, we're going to get into more details in the next like 20 minutes. But that was just to like kind of build some intuition that you're going to want that alpha hat, you know, you would like it, although its expected value is actually alpha, any particular flip can differ from alpha, of course, and you'd like it to be really like concentrated or close to alpha every single time, if you could. Okay, so let's draw a plot of a potential experiment we run and see how this variability can occur, just to really drive the point home. So the y-axis here is going to be your experiment. And the experiment is you flip the same coin 5 times. And so what you're going to do is you're going to do experiment number 1, which is you're going to take your coin and you're going to flip it 5 times. Okay. And then we're going to plot what is the corresponding flips we got and what is the calculation we got for the sample mean. And then we're going to take that same coin and flip it another 5 times, a different 5 times. And that's going to be like experiment number 2. Experiment number 3 is same story. But what I want to just show you is that you can really get different values for your estimate. And we're going to want to ask how much can that vary. Okay, so there's some values on the x-axis. So this is 0. This is 1. And of course, when you flip the coin, you're only going to get heads or tails. So let's do some examples of flips. So first experiment. Maybe I flip the coin, I get tails. And okay, let's make some assumptions here, right? Which is the things I've done in this plot is going to be that n equals to 5. I have 5 coin flips. And I'm going to say that alpha, the true parameter, is actually 4 over 5. Or 80% of the time, you get heads. Okay, so now let's flip this coin. Flip it 5 times. Okay, 80% chance you get heads. Maybe first time you still get tails. Then the next 4 flips maybe are sort of reasonable, and you get 4 heads in a row. So these x's should all be on the point 1, and I'm just making it kind of more clear that you got the same value 4 times. Okay. So that's your 5 coin flips. And you go ahead and you calculate alpha hat, right, which is the sample mean. Well, what would that be? You would sum up those values and divide by 5. So you take the number 1, sum it up 4 times, and then you add 0, so you get 4 over 5. And so your estimate alpha hat would be somewhere around here, which is 4 over 5. That's going to be your estimate. I put a big point here. And that's like the black alpha hat, which is equal to, right, I'm just going to write it in maybe like 0 plus 1 plus 1 plus 1 plus 1 over 5. Okay. So now let's do a similar story. Like, once again, I'm just making up things, but like, imagine you flipped the coin again 5 times. Well, it's very possible that you got tails maybe again. Then you got heads. Then you got heads. Then you got tails. Then you got heads. And so now if we do the calculation, we notice, okay, like in this case, alpha hat really did equal to what we wanted, which was 4 over 5, right? And I'll take the question online in just a moment. But so here we actually, our alpha hat really was the true alpha, because, you know, if there's a 4 over 5 chance of getting heads and you got 4 heads and 1 tails, it's like what you would expect. But you could get this outcome, which is 3 heads and 2 tails. And here, what you will find is that now, if you'd calculate alpha hat, you get 3 over 5. And so alpha hat would be like here, this is alpha hat. I'm not going to write that calculation again, but it would be like 0 plus 0 plus 1 plus 1 plus 1 over 5. And let's just, to drive the point home, let's do it again. Imagine experiment 3, you got 5 heads, which is totally possible. Now your alpha hat is like right here. And alpha hat equals to 5 over 5, which is 1. Notice that's not alpha. And then one more time, suppose you do the experiment and you get really unlucky, which is totally possible. And you get 4 tails and then 1 heads. And so now your estimate of alpha hat will be somewhere around here. And it will equal to 1 over 5, which is terrible, right? It's quite far from the true alpha. And this is to just show you that, you know, for any particular flip of n coins, you could get very unlucky. You could literally get tails every single flip as long as there's some probability of it. And then this estimate is going to be quite poor, right, in that case. And so we want to somehow, like, talk about this. Like, well, like, intuitively, the likelihood of something like this happening is very low. Or like the probability of that happening is quite low. And the probability that these alphas are like close to the true alpha, right? This is like, the true alpha is indeed over here, right? 4 over 5. This is like the true alpha. We would expect that if we were to do this like over and over and over again, n times, that, you know, you'd get a lot of like, okay, well, you'd get a lot of points that are like here, and occasionally, like very rarely, you get something out there. And this is somehow like the variability, right, of alpha hat. And we have a term for that called the variance. And so now, hopefully, when I write something like, we're going to calculate the variance of alpha hat, that isn't so confusing, weird, or shocking, because alpha hat can change. It's random. And so we're just going to ask, how far does it vary from its true expected value, which we calculated above as alpha. Okay, so we'll do that calculation in a moment, and you'll see we use both of these properties, which is that this is Bernoulli and this is independent. And you can already start to see why in supervised learning, we assume that things come from the same distribution and they're independent. We're going to see that. Okay, and now I answer the question online. And the question online asked, how in the world did we get n over n here when we had 1 over n over here? Something like that. And the answer is, once again, let's just look at this step. So maybe I point out some things. Okay, so this step is easy. Obvious, it's like you take the scalar out. This step here, use the linearity of expectation, and maybe I just write that. This is like a property, it's called linearity of expectation. It will be on your formula sheet. This next step, what it does is it looks, okay, this is a number, right? The expected value of xi is a number. The expected value of each xi could be a different number, but turns out it's not, because each xi has the same distribution. And so its expected value, if you expand it out, you'll notice is equal to like the sum of the values, the outcomes, times its probability. And since all the probabilities are the same, I can plug in any random variable, any of the xi's in here. I just pick the particular one, x1. And so this step used the fact that they are identically distributed. Okay. And then after this, you just notice that this is just a number, and you're summing a number. Like an example is, you take the sum of I equal 1 to n of like the number 2. Well, what does this equal? This equals to n times 2. And so that's all we did. We took this number, we multiplied it n times. That's where this n came from, and you get n over n. Okay. Maybe that was a very in-depth explanation of something completely obvious. But okay, let's get back to our story. So let's calculate the variance of this guy. And what should we get? Like, before you do a lot of calculations, probably a great idea to just think about intuitively what you would expect to get here. And what you would expect is something like, well, I'm going to get some variability. Okay, that's going to be some number, let's say. But what happens as I increase n, right? As I increase n, I'm going to have way more coin flips. So let's say I had like 100 coin flips. It's very, very unlikely, right, that I would get that, in this case, for 100 coin flips, that would be that 80 of them were tails, and that 20 of them were heads. And if you increase n to like 1,000, it's probably even more unlikely. So somehow as n increases, we're going to expect that the variance from the true sample mean is going to get tighter and tighter. Okay, so that's what you should expect to get somehow. And now let's see if we get it. So in here, we're going to use the properties of variance instead of expanding out this variance, which is like the square difference of your random variable to the expected value. That would be quite horrendous to write all this. Instead, we're going to use the properties. So first of all, we write down what does this actually mean. And that means plug in alpha hat, which is 1 over n times the sum of x1 plus up to xn. Okay, now let's use some properties. First property, just like the expected value, there's this property where if you have a constant inside the variance, multiplying a random variable, you can take it out. However, if you recall, the definition of variance squares the inside random variable. So there's going to be, this constant is going to get squared as well. And if you just write out the definition, you'll see that this is kind of obvious. Okay. And so now we've taken out the constant, which is good. All right. So now we've got this kind of ugly looking thing still. And the way we address this in the expected value case, right, where we had this sum, is we're like, oh, well, the expected value of a sum of things is equal to the sum of the expected values. That's just always the case. It's the linearity expectation. You don't need any properties. It just always holds. Variance is not the case anymore. However, there is a property in the probability notes, which you will also get on your formula sheet, saying that if you have the variance of a sum of random variables and they're independent, this is where the independence is going to come in, then this is equal to the sum of the variances of each one of them. Beautiful. So this is going to use independence. Which we have not used up to this point. And this is going to tell us that we have 1 over n squared times the sum I equal 1 to n of the variance of each one of these xi's. And now the story is really the same. Well, you look here, and then you notice that if you expand the variance, it's going to depend only on it's going to be this sum of outcomes times the distribution. every xi has the same distribution, and so the variance of every xi is the same as the variance of x1 or x2 or so on. And so you have the same story, which is you can replace the variance of xi with the variance of x1. And then this is a sum of a constant, so you get n over n squared, variance of x1, which is equal to 1 over n times the variance of x1, which is the same as the variance, okay, dot, 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 it's the same as 1 over n times the variance of xn. And okay, fine. Each one of these, like x1s, is this flip of a coin. It has some variance, just like a regular coin has some variance in its flips. That's just a number. I'll tell you what it is. For the Bernoulli case, it turns out to be alpha times 1 minus alpha. Fine. That'll change depending on your alpha thing. We can talk a little bit more about this in a second, but the important thing is that you notice that there's this 1 over n out front. So now let's go back to what our intuition said, right? Which was like, what is the variance of our sample mean estimate? Well, it should go down as n increases, and this is exactly what we see. We see that the variability in the outcomes of a particular, like a particular flip of n coins, is going to decrease as n increases. So if you flip more coins, you're going to get tighter and tighter for mean. And okay, so that's going to tell us maybe in some sense that this sample mean estimate is indeed a good choice. And we're going to want to gather, okay, like what are some things? First of all, sample mean seems sort of reasonable, has the correct expected value. And as we increase data, we get this property that, you know, it's getting tighter and tighter. And I'll draw a picture for this in a second. And this also tells us a very important thing, which is that we want to gather as much data as possible. Like more data just really doesn't hurt, and that's going to be the same story in machine learning. And you might hear a lot about, you know, in the real world that companies, like super important part is getting more and more data. Like really, if you get more data, things will get better. It might not always be the best way of using your money to improve your model, but it will improve your model to some extent. Like it will improve it. How much it improves it? Well, there's diminishing returns, obviously. If you have like 10 billion flips of a coin, it's not probably going to help that much if you have 100 billion. Okay, and this has another, like this story has like what is called an asymptotic view, which is like okay, let me just draw it. So you can plot this kind of thing, and what I mean by plot this kind of thing is you can plot, you know, the PDF. So okay, let's talk about this. Alpha hat is a random variable. It has a corresponding distribution, right? And of course, and it's a continuous random variable because it could take any number between 0 and 1. And so it will have a PDF. So we can draw its PDF. And it turns out that people found out that the PDF has a very nice form. Okay. And the PDF turns out to be the following. And so first of all, so to figure out what the PDF is, I'm going to actually tell you the distribution, and it's a distribution we know, and since it's a distribution we know, we can use the PDF we know it has. So here's so we have a distribution of alpha hat, and I'm just going to subscript it with n now to indicate this is like alpha, the sample mean for n coin flips. It has the distribution of approximately, and this gets better and better as n increases, approximately the normal distribution, or the Gaussian distribution, right? And what is this Gaussian's mean? Well, the mean of the Gaussian is the expected value of alpha hat of n, which we saw is just alpha, and the corresponding variance is going to be the variance of what we just calculated, which is the variance of alpha hat. Oh, that's a big eraser. Okay, the variance of alpha hat, and we just calculated that, and we saw that that's equal to 1 over n times the variance of any one of these x's, such as x1. Okay, so now let's draw the PDF for the corresponding normal distribution, and we will learn some things. So, if in the case where you have the 5 coin flips, we'll find that it's like fairly spread out. Okay, this, first of all, important property, its expected value is around the actual true mean. So that's going to be alpha. Let's put that guy over here. And now for the case of alpha, let's say 5 coin flips, we'll see that it's like a fairly spread out distribution. So this is going to be the corresponding PDF of alpha hat of five coin flips. And now let's see what the story looks like when we increase the coin flips. Let's increase it to, say, 100. Things are going to get tighter. And this says it's more likely you're going to get a value for alpha hat that is really around this. And this shows you how the variability changes as well. So it's PDF. This is the PDF of alpha hat of 100, let's say. And then if we take it to the extreme where we like take it and make it 1,000 or like 10,000, you'll get something really tight. And in the extreme, you actually get like an exact point here. And okay, so remember the area under all of these has to be the same. So if I have a really tight guy, then the height of it is going to have to be massive. And I'm not doing it justice how tall this should be. Okay, that's what the story looks like. And this will be something like maybe the PDF of alpha, let's say, I don't know, 10,000. Okay, so that's the story. And we saw this, right? We saw that the variability decreases as n goes up. That means that the PDF gets tighter and so on. Okay, so all this stuff is, okay, so that's the story of the coin flip. Is there any questions about the coin flip? Because after this, we're just going to do the like almost obvious mapping to our random losses. Okay, great. So here's going to be the story. So what do we want to do? We want to estimate the expected loss, right? So estimating the risk or expected loss. Notice how this is very similar to estimating the expected value of a coin flip. Great. How is this going to work? Well, what do we have? Or what's the story? The story is something like you have a new, let's say, a new feature label pair comes from this distribution P of X, Y. We've seen this a bunch. Yeah. So it comes from this distribution. Then notice that, you know, if you have some fixed predictor, so let's fix F, which is a predictor from X to Y. Right. Then, okay, so some things to note. These are random variables. F of X, also a random variable. And you might get annoyed that I'm stressing this so many times, but this is very important to drive the point home that if you then take the loss function, okay, let's just remove the z for now. If you take the loss function and you plug in f of the random feature and you compare it to your random label, that's still a random variable. Great. And okay. What do we care about? We have all these things. What do we care about? Well, we care about the expected value. We care about this guy, right, which is L of f. This is equal to the expected value of a random variable. Which random variable? This guy here. And this is the thing we've seen before. Okay, so let's just understand what happened here. We have an expected value of a random variable, this thing. We would like to know it, but we don't. Just like the coin flip case, we'd like to know the probability of getting heads, but we don't. There's a little bit of a step here, right, which is that we have samples of x, y, and we've plugged them into a function and then another function. But that's all fine. This still gives us a random variable, and we'd like to know what this is. How are we going to do this? Well, we're going to do exactly what we did with the coin flip, right? Which is we're going to want to get n estimate, or like n samples of this random variable. And all that's really going to mean is we want to get n samples of x and y and plug it into this corresponding function, and we'll have n samples of that random variable. And unsurprisingly, we have this data set, right? So what do we have? Okay, and importantly, we don't know this, right? We don't know this. So we don't know this guy. We want to estimate it. Let's estimate it using n samples. Okay, so what do we have? We have a data set. The data set is like this. Remember, we had these like in the coin flip case. We had these like x1, x2, whatever up to xn. Well, now we have I'll write it multiple ways. I'll write it as like the way we've seen it before, which is you have x1, comma y1. This is your first feature label pair. And you have this up to xn, yn. Right? This looks like the n coin flips. If you do the mapping, which is, let's call each one of these guys, let's call each one of these equal to z1 and the corresponding indexes for the data point. So I can write this equally as like z1 up to zn. Okay. So actually, let me not do this yet, because those aren't quite the random variables we want. Just to make the mapping clear. Okay, so you have this data set. And of course, for each feature label pair, we can use that feature label pair, plug it into the loss function with our predictor, which we have, right? So we've fixed some predictor. We have this loss function. We've chosen it to be like the squared loss or something. We can, of course, take each one of these data points, plug it in. That's going to produce a new sequence or like set of n random variables, not equal to the above thing, but you get this new sequence, which is like the loss of the function, the predictor of x1 compared to y1, right? This is your first random variable, and so on. So you can construct like what is, I guess, a new data set of losses, of n loss samples. Okay. And this is crucial because after you have this, the story is essentially done. So this is the important thing. We've constructed this new data set of n samples of our loss. And just to make the mapping a little more obvious, if we called each one of these like z1 up to zn now, well then it would look something exactly like the coin flip case, where the z's are now like the random coin flip kind of cases. Okay, and so now, based on this property, we can, like all the tools above, they didn't need to just be for Bernoulli distributions. It didn't matter what the distribution was. Everything holds in the exact same way. The only thing that was important was that things were independent and identically distributed. And that is an important fact to note. So each one of these, so you had this data set, and the property, right, that we had was that these random, let's forget about that z. That z really shouldn't. Okay. So each one of these random variables, x1, y1, is distributed the same, x, y, and they're independent and independent. Oh, each one of the xi's. Okay, and just to quickly answer the question online, someone's like, just to be sure, the alpha in the previous things was the average or like the expected value of the coin flips. The answer is yes. It's the expected value of any coin flip. Okay. And okay, back to the story. So you have this data set. Each one of these feature label pairs come from the same distribution and they're independent for all I. And then we constructed this new data set, which is like these losses, we call them zi's, and we can, it turns out that the mapping works exactly the same because these are just, like each one of these things, these losses and f's are just functions of x1 and y1, and so these things themselves as random variables are independent of each other as well. Okay, and so the story is that similar to above, you can write L of f of x I, yi. That's a random variable. It comes from some distribution. We're not going to care about it, but it has some distribution, which I can label with, let's say, L of, just to make it very explicit, it's going to be the distribution for like this. Okay. And they're independent. And I'm writing out things very explicitly so that the mapping is hopefully obvious. And so now we have n independent samples, which are samples of our losses. And we care about L, this expected value. So if we want an estimate of it, the first thing we're going to do is use this notation where we use a hat above L of f to mean it's an estimate of L of f, which is just a number. Now this L hat of f is going to be a random quantity, right? And it's going to be the average of our n samples of the loss. Okay, right? So you have these n random samples, It could have been who knows what. And so we do this calculation, which is now going to be, we're going to use the sample mean, so that just like we saw above, so that'll look something like you take L of F of X1. Here, let's write it in a nice summation notation. So we'll use sum I equal 1 to N of our random samples, which are L of F of Xi, Yi. All right, we take this guy and we divide by N. And it turns out that this thing, just like above with the coin flip thing, all the properties hold in the exact same way. And so what that means is we can talk about what is the expected value of L hat of F. Well, that expected value turns out to be exactly L of F. As we saw above, it's the same steps. Like literally, you would just write the expected value of this object. You would then be like, oh, I can take out the constant. I can then apply the expected value inside. So I'd write the expected value in here. All of them have the same distribution, so I can plug in 1 here or whatever. And and then yeah, and then you get this guy here, which is just the expected value of this. Okay, so and maybe just to make this just absolutely clear, notice that this is exactly equal to the expected value of this little guy inside here, right? Yeah, it's the expected value of the guy inside here for any single x you would want to choose. So you can pick like x1 or x2 up to xn. And so I don't know why I got confused, but we return with the exact same definition of this, except here we usually had like an arbitrary x and y. But now we can replace it for any one of the x's and y's in our data set because they all have the same distribution. Okay, that's good. We have this property that our estimated expected value of our loss estimate, which is this is the empirical risk, is equal to the true risk. And you can also talk about this variance. And the story there is also the same. And that is that it becomes 1 over n, right, times the variance of any one of these, plug in any one of the feature label pairs you want. And the important property is that as n increases, the variance goes down, and so we're going to get more and more likely any particular n samples of a data set, any particular data set of size n will be closer and closer to this as n is larger. So you want to gather data sets that are as much data points as possible. Okay. And so, yeah, that's the story, which is we want n large because things just get better. And now I end you with like a bit of a cliffhanger that we will only return to in like 3-4 weeks, which is that there's a problem here. And that is the fact that all of this was for a fixed predictor, right? It's like you're like, okay, I only care about this line here. Maybe that was like a bad line. And you're like, okay, like I can clearly, like I can do this, get all the data points, get all these measurements of how far the things were, like from that plot I showed earlier or whatever. And I can get a good estimate of its corresponding, like, expected loss of that thing. But here's the problem. Like the story was something like what I just said again, is like you fix this thing, then you go gather n data points, and then you're like, okay, these n data points, I'm gonna just like plug them into my function, my loss, and take the sample, the average, and everything will be fine. But this is not what we are doing, right? In ERM, what's gonna happen is that we're gonna gather the data set first. We're gonna have a bunch of functions, that's our function class. And then we're gonna cherry pick the function in our function class that best fits the data, right? And so there seems to be some problems here, which is now that, in other words, this f is not fixed beforehand, but it actually depends on the data. Okay, so let's make that a little bit more clear. And this is a very deep problem with a lot of consequences that we will study later on. But I just want to make clear, like ERM, right, is this thing where you have this learner, you pass in this random data set. It outputs a random predictor of hat. This thing will change with data. And the question becomes like, well, did all this above kind of still work the same way? And the answer is kind of, but like not really. And let's see what went wrong. Well, what went wrong is, right, to get all this stuff to work, we needed all these guys to be independent of each other. But now, f itself is a function of all the data. So just to make this like a little bit more clear, like this L now with f hat would be like you plug in A of D, and remember D is literally takes in all of these things. And then for that guy, you calculate the corresponding loss. And this seems a little precarious because now these are definitely not independent. No matter which xi you pick, the corresponding predictor depended on all the other ones. So they're all correlated and so on. And yeah, that's going to cause some problems. And we're going to see that the thing that kind of trades off how good things work. Okay, so yeah, you have this ERM thing, and then roughly speaking, the question was something like, oh, well, you know, if I have like L hat of this F hat now, which depends on the data, is that really like so close to this L of F hat, like the true expected thing, in the same way as above? And the answer is like, okay, it will depend on two things, and I'll give you some intuition on why. It will depend on, well, let's think about what the two things are. So like, remember this example I just gave you? Where is it? You know, which is like we fix this F. And then after that, we gather data. But we're doing it kind of the other way. We gather data, and then we say, oh, we pick the best function in our function class. So there's kind of two extremes. And I've said this before, but if there's anything that you learn from math or anything, like I think one of the best ways, and a lot of people say this, is just think about the extremes. And if the extremes work out, then you probably get the intuition of everything in the middle. So let's try these extremes. So suppose that the set of functions that we consider after we see the data is like just a set of function, which is just one function, right? So your function class contains exactly one function. And you fix that before. Your function class is like, okay, I'm only going to consider this one line. And then you gather your data, and you're like, okay, let's pick the best function from my function class. You only had one function to pick from. Turns out that's exactly the same story as this, and you're good to go, and everything works just like we've seen. Let's take the other extreme now. Your function class is literally every single possible function. We saw there's some problems because of the no free lunch theorem before, but let's imagine we didn't care about that. We have this function class, all possible functions, like all these polynomials and so on. Now we gather the data. You can imagine that there's going to exist a function that like perfectly fits every single data point. It's going to look weird and distorted and everything. And the chances that that does well on new data is very, very unlikely. Okay, so these are the two extremes. And so this is to highlight the point that it's going to be very important. And it will depend, this choice, or like how good of an estimate this thing is for a random predictor that we pick. It will depend on the function class. Okay. And then the other thing it will depend on is the amount of data. And roughly speaking, it's like if you only had like 2 data points, well, you can like super easily find a function that fits both of them perfectly, but it might be terrible. So like in this, like, okay, super roughly speaking of this plot, if your data points, like if the data points really should look like this, but you only gained 2, and maybe you got unlucky and you got a data point here and another data point here, well, then you can imagine even if you're considering lines, then you're going to get this like terrible line that fits a data perfectly, but does terrible on new data. But if you get more and more data points, you're going to find that, well, this line doesn't look so great anymore. And actually, I'm not even going to be able to fit it perfectly, but then something like this will actually work fine. Okay, so the quality of our estimate will depend on the function class and n. And it depends on n in the same way as we've seen before, which is more data helps. However, the function class story is more complicated, and we'll discuss this later. And this is usually called like model selection or architecture selection or something like this. And that's going to be this whole story of like, should we search over lines? Should we search over polynomials of a higher degree? Should we search over gigantic neural networks? And we'll see what the math tells us about that. Okay, we end here. Oh, and then maybe one last point I wanted to say is for the next part when we get into optimization and so on, we're just going to use this estimate, this sample mean, as I have described it, and we're just going to assume that it's fine and it's good enough. And this is exactly what people use in practice. They use the data to estimate the expected loss, and then they try to minimize and find the F that makes this as small as possible. Okay, and so see you next week.